Hello, students. Welcome back to the channel. In today's lesson, we're going to be looking at Newton's law of motion, and we are dealing with the four cases of normal forces. So without any further ado, let's just get right down to the lesson. Okay, so here we have the definition. So normal force says it's the force which a surface exerts on an object which it is in contact and which is perpendicular to the surface. Then we have another definition, it's frictional force. We say this is the force that opposes the motion of an object and which acts parallel to the surface. Then we have static frictional force. We say this is the force that opposes the tendency of motion of a stationary object relative to a surface. Then we have kinetic frictional force. We say it's a force that opposes the motion of a moving object relative to a surface. Then followed by Newton's first law of motion, we say this is an object continues in a state of rest or uniform velocity unless acted upon by a net force. Then we have maximum static frictional force. We say maximum force that can be applied to an object without it moving, right? Then we have Newton's second law. It says when a net force is applied to an object, it accelerates in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass of the object. Then we have Newton's third law of motion, which says when object A exerts a force on object B will simultaneously exert an oppositely directed force of equal magnitude on object A. Right, then we have Newton's law of universal gravitation. It says each body in the universe attracts every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Then we have the last definition, it's weight. We say this is the gravitational force the Earth exerts on any object on or near the surface, right? So as it comes to our definition, that's all the definitions that you have to figure out under Newton's law of motion, right? So now let's proceed to the main section of this video lesson, which are the four cases of normal force. This video here will just be looking at all the cases that will be given in terms of our exam, and then see how we can best tackle those, right? So it is best that you understand all these four cases of normal force so that you'll be able to perform calculations. So with this exercises here, or these examples, we'll just be going through the formulas that you need to have in order to calculate the normal force. And after calculating the normal force, we'll try to calculate either the frictional force or the coefficient of frictional force, right? So in this case here, we are given case number one, which is the first case of all the four cases of normal force. In case number one, you might have that the force is applied horizontally, or your object is just moving horizontally like that, right? So in this case, you have to note that if we were to draw a free body diagram, so the first thing that we have to do is obviously try to indicate a free body diagram showing all the forces that will be acting on this 8 kg block. So because we know that this 8 kg block is on the surface, we know that it would be experiencing the normal force, because remember we said normal force is the force that is exerted by the surface on an object that is in contact with, right? Then down there we have the gravitational force. So it's always acting downward. And then in that direction, we can see that a force is being applied. So it's a pulling force. Then this is force applied. But then knowing that frictional force is the force that opposes the motion of an object, then this side here, we will have frictional force. To be more specific, if this is moving, we have kinetic frictional force. Now, these are all the forces that are being experienced by this 8 kg block. But then now, let's say number one, the case would be how to calculate the normal force. So remember, we are dealing with the cases of normal force. So how would we calculate the normal force? The normal force. In this case, we can see that the upward forces will have to be equal to the downward forces. So in this case, it's just simple. You just take your Fn and then simply equate it to Fg. In other words, that means if you are looking for the normal force here, you'd have to know what is the gravitational force. But then we do know that the formula to calculate the gravitational force is just simply mass times the gravitational acceleration. So that means this is the formula that we'll be having in terms of calculating the normal force if the force is being applied horizontally like that. Now, obviously, our calculations would be like this. Since we are given the mass 8 kg, that means we'd say the normal force is just simply 8 multiplied by the gravitational acceleration of 9.8. Then simply punch all of that into your calculator. Then you get 78.4 newtons, right? Okay, so nice. That's our normal force. Now, let's suppose that we are given the coefficient of kinetic friction. So, coefficient of kinetic friction. So, kinetic friction, which let's say we are given that our mu k, so mu k is the coefficient of kinetic friction. Let's say we are given that it is 0.16. And then the next calculations say we must calculate the frictional force, right? Calculate the magnitude of the kinetic frictional force. Now, the formula to calculate that is simply Fk is equals to mu k multiplied by the normal force. Now, since we have already calculated the normal force, it's just a matter of substituting the coefficient of kinetic friction and then substitute the value for the normal force, 78.4. Right. And then we just simply have to punch all of this into our calculator. 78.4 multiplied by 0.16. And then we find that the magnitude of the frictional force will be 12.54 newtons, rounded off to 2 decimal places. Right. So this is how you'd be calculating the normal force and also the frictional force, provided that you have case number 1, whereby the force is just applied horizontally and then your object is just moving horizontally without any forces that are being applied diagonally or at an angle. Then, okay, let's now move to case number 2. So with case number 2, this is what we have. We have a situation whereby an object is pulled at an angle. As you can see here, the arrow is outward, indicating that this is a pulling force. So it's a pulling force, and then it is being pulled at an angle of 50 degrees, right? Relative to the positive x-axis. Right, then now, in order to calculate here, the first thing that we have to do, obviously, is to draw our free body diagram. So the free body diagram is very, very important in terms of the calculation. So we have Fg going downward as always, then our normal force going up there because this is on the surface. Then our force is being applied at an angle. So what we do is that we take it exactly as it is, then put it here. And then we can indicate that. And then opposing the direction of the motion is your kinetic frictional force. Note that your Fk will always have to be parallel. It has to be parallel to the surface, right? It is parallel to the surface, right? So you do not draw your Fk like this. It is very incorrect to draw your Fk like this. Your Fk always has to be horizontal because remember, your Fk does not oppose the force applied, but then it opposes the motion of an object. So the motion of this object is just going to the right horizontally. So that means Fk has to go to the left horizontally. Right. And then, okay, so if we ought to indicate the angle, then we can indicate it here 50 degrees, but then it is not necessary unless you are told to indicate. Right. Now, in this case here, if we wanted to calculate the normal force, we'd have to understand that this goes as Fn is equals to, now, if this is pulled, then we have the gravitational force Fg minus the horizontal component. Now, how did I come to this? Now, let's follow through. Remember that we do understand that if a force is being applied at an angle, according to our vectors in 2D, we know that if a force is diagonal like that, you can actually resolve it into two components. The two components we are speaking about, that's your Fx, which will be the horizontal component, and then also Fy, which will be the vertical component, right? Now, since this is being applied at an angle diagonally, we know that it occupies the first quadrant there. So that means we must have our vertical component going up there. And then this line here will indicate the horizontal component. So to represent the force applied here, we have Fy and Fx. But then right now we do know that upward forces, they're always equal to the downward forces. So if we had to form an equation of the upward forces equal to downward forces, then we do understand that the kind of equation that would have is that Fn plus Fy would be equals to Fg. So the sum of the normal force and the vertical component will be equivalent to the magnitude of the gravitational force. But then remember, we must make our normal force the subject of the formula. Therefore, we'll end up having normal force is equals to the gravitational force minus the vertical component. So you have to note this formula right here as the formula that we'll be using to calculate the normal force if we have a situation whereby the object is being pulled at an angle, which is case number 2. Now, obviously, to break this one down, you have your Fn. Your Fg is still the mass times the gravitational acceleration, but your Fy, remember, it breaks down to F sine theta. Right. Now, in this case, how would we calculate the normal force? To calculate the normal force, we would simply have to consider this formula here. Fn mg minus F sine theta. Then we have our mass as what? The mass is 45 kg as given there. So we have 45 multiplied by 9.8 and then minus our force. The F here is for the given force here, which is 90. Then we have 90 sine theta is for the given angle there, 50 degrees. Now at this point, you simply just need to punch all of this into your calculator, aka umshinwe ibalo. Then 4.45 times 9.8 minus 90 sine 50 degrees, right? And then we have our value as 372.06 newtons. So this is the magnitude of the normal force right there. Right. Now, obviously, if we have that as our normal force, if again we are given that the coefficient of kinetic friction, let's say this time around it's 0.2, and then we are supposed to calculate Fk, then we'd say Fk is equals to mu k multiplied by n, and then we just simply say 0.2 multiplied by the normal force that we have calculated here. And then when you punch that into your calculator, so we have 0.2 times 372.06. And then when you punch that into your calculator, you get 74.41 newtons rounded off to 2 decimal places. Right. So this is how you would calculate the normal force if the object is being pulled at an angle, right? So make sure that you note this formula here as your case number 2, right? So it's the normal force is equals to Fg minus Fy, which breaks down to mg minus F sine theta, right? Now let's go to case number 3. In case number 3, we have a case whereby the object is being pushed at an angle. Also, you have to note here that you would calculate your normal force differently, right? So the first thing that you want to do, obviously, is to draw your free body diagram. Now, we already know the obvious forces. That's your Fg always going downward, and then your normal force going upward like that. And then here, we have, since this object, if it's being pushed like this, it will be going to the right. That means the frictional force would have to oppose and go to the it will be going to the left, meant to say. That means the frictional force have to oppose and go to the right. Now look at this. We can see that our force is being applied at this angle of 15 degrees, and then this is a push, right? It is being pushed at an angle. Now you are not supposed to change this, but then what you cannot do is to draw it like this. Right. So this is incorrect because remember, with the free body diagram, you cannot have an arrow pointing to the dot here. You cannot have an arrow pointing to the object. All the forces must be outward from the object because these are the forces that are being experienced by the object. So that means in that case, you'd have to draw this one here. So you do not change anything. You just simply take it as it is, cut it and paste it right here. So it's just a cut and paste method. And then you indicate this is your force applied. Now you have all your forces like that. But then again, you would have to understand that it is being applied at an angle, right? So your force is being applied at an angle. That means it must resolve into components. Now resolving that into components, that means down here, we'd have our vertical component, and then going to the right, we'd have our horizontal component. So this is horizontal component and this is vertical component. And as you can see here, it corresponds to that because the FA is going downward, and then that's why your force, your vertical component goes downward. And then if you can check in terms of the horizontal movement, it is going to the left. So hence we have our Fx going to the left. Now when we calculate here, the formula for the normal force will now become like this. If again we consider the fact that our upward forces need to be equal to the downward forces. Right now we can see that the only upward force that we have is the normal force. But then we have two downward forces, which is your Fg plus the Fy. Right. So that means in a case whereby the object is being pushed at an angle, you have to add the gravitational force and the horizontal component. But in a case whereby it's being pulled, you have to subtract the vertical component from the gravitational force. So note the difference there. So that's your formula for case number 3. And then now you have a Fn is equals to mg plus F sine theta and then there we go. So our mass here is 3, and then we have our gravitational acceleration as 9.8, and then plus our force here is, as given here, it's 30 newtons. So we have 30 and then sine 15 degrees, right? Now at this point, you just simply need to punch all of that into your calculator. So there we go. Then we get what? 37.16 newtons, right? So this becomes the force thereof, right? And then if we wanted to calculate, let's say this time around, instead of calculating the magnitude of the frictional force, we are given the magnitude of the frictional force. Let's say they say our Fk is equals to 10 newtons. And then now they want us to calculate the coefficient, right? So remember, we can also have a case whereby we are now looking for the coefficient. The formula is still the same. It's Fk is equals to mu k multiplied by n. Now that means we are given the Fk, it's 10, right? And then the mu k, that's what we are looking for. But then remember, we have calculated the normal force. That's 37.16. Now calculating the mu k, that means we have to divide both sides by this 37.16. And then we find that our coefficient will be equals to what? So if we can just simply say 10 divided by 37.16, then we're going to find our value as 0.27, rounded off to 2 decimal places. 0.27. Then nice. Okay, then let's now proceed We have case number 4, which is the last case of the 4 cases. It says this is a situation whereby the object is on an inclined surface. So what you want to do first is to draw the free body diagram. Now you will understand that with the incline, we have the gravitational force being resolved into 2 components. So what's important is that Fg is resolved to 2 components, right? And then these 2 components are namely, number 1, Fg parallel, which is your parallel component of weight. Parallel component of weight, right? And then we also have number 2, Fg perpendicular, which is obviously the perpendicular component of weight. Perpendicular component of weight. Now, this is very simple. What you need to understand with your Fg parallel is that it always slides down the surface. So this one always slides down the surface, slides down the incline. So that means in a case whereby your incline is like this, you already know that your Fg parallel will slide down like that. And then this one is always perpendicular to the surface. Perpendicular to surface, facing down. So this is perpendicular to the surface facing down, meaning that in all the situations, you'll always have to find your Fg perpendicular being like that if the surface is like this. But then in a case whereby you have a surface like that, an incline like that, then again your Fg parallel will have to slide down the incline. And then obviously your Fg perpendicular would have to be perpendicular to the incline, right? So you always have your components like this. Now, why do we resolve into components? It's because when we resolve into components, that's when we are able to calculate the normal force clearly, right? And then, okay, in this case here, we do know that the normal force would have to be perpendicular to the surface. Because the surface is inclined, then we do understand that we must have something like this. So if I can just erase here, and then let's have our drawing. So there we go. Our normal force will be perpendicular to this inclined surface. Remember, it must form 90 degrees with the surface, right? So hence it is now slanting like this because relative to the surface, it must form 90 degrees. Then straight in line must be our Fg perpendicular. So the normal force is always straight in line with the Fg perpendicular. Then sliding down the incline will be your Fg parallel. And as you can see, it must be parallel to the incline, right? Then up there, we can see that we have our force applied. So this is our force applied. And then we know that since the object is being pulled upward here, we must have an opposing force, which is the kinetic frictional force. So down the slope, we have Fk and Fg parallel. So now, in order to calculate the normal force, we have to understand that the upward forces are always equal to the downward forces. Upward, we only have the normal force, and downward, we have Fg perpendicular, which brings us to this case. That means case number 4, you have to note that your Fn will be equals to Fg perpendicular. Note that this only happens on an incline. Then this is Fn is equals to the Fg perpendicular. The formula is like this. So for Fg perpendicular, it's always mg cos theta. And then for Fg parallel, it's always mg sine theta. So these are the formulas. Now, do not confuse them with fx and fy. With fx, we know it's f cos theta. And then with fy, it's f sine theta. So these are not the same. This here are the components of the applied force, and this here are the components of weight. Then this is mg cos theta, right? So that's the formula right there for case number 4. Now, if we wanted to calculate the normal force in this case, we'd simply say, what is the mass of this? And then as we can see here, we are given a 5 kg. Yes, 5 kg. And then we have 5 multiplied by 9.8 and then cos 30 degrees. Now the theta will be found from the incline, right? So it is the angle of the incline. Then 5 times 9.8 cos 30 degrees. Then when you punch that into a calculator, you get 42.44 rounded off to 2 decimal places, right? 42.44 newtons. Now, if in a case whereby we are given that our Fk is equals to, let's say, 15 newtons, and then we are supposed to calculate the coefficient, then again here we can say Fk is equals to mu k times n. Then our Fk is 15 newtons, and then we can simply calculate our coefficient by substituting the n there, 42.44, and then if we divide both sides by this 42.44, and then like that 42.44, then we're going to have our coefficient as what? So let's just go 15 divided by 42.44. That's going to be 0.35. And then there we go. So that's basically how you would calculate the normal force and the kinetic frictional force. So make sure that you come back to this video, watch it as many times as possible, try to understand all the 4 cases of the normal force, right? So that when you tackle your exam, you are able to identify these cases and apply the necessary calculations into that. So with all that being said, please press the thumbs up button and then also share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.